Hey guys, this video is meant to go along with the packet, so if you don't have the packet already open, you are going to want to open it up and either work in Notability, work on a notebook, print it out, anything is kind of up to you, but the video and the packet go side by side. Right now, my dog is sleeping next to me and she's snoring, so if there are any weird sounds in the video, I'm going to blame it on her. So the point of this packet, the point of the work block is to learn about the fundamental theorem of calculus, which we started, but we didn't finish. So the first part we're going to talk about has to do with derivatives. The idea is that the derivative and the integral sort of undo each other, right? Like taking the integral is to take the antiderivative, and then if you take the derivative of that, you're just going to go back where you started. To explain the way this is written a little bit, the reason why we have an x on top of this integral is because if we had a number, if there was a number up here, like the integral from a to b, or the integral from 1 to 4, let's say, then the entire integral would have a numerical value. That's something we could plug into our calculator and get a number for. But if we want to take a derivative, this can't be just a number, we want it to be some equation. So that's why we have an x on top up here. And we have a t here. This is actually just called a dummy variable. It doesn't matter what letter is here, just as long as this letter, the t, is different from that letter, the x. So it's really just called a dummy variable, and it's only there to be different. So this first part, this first equation, this whole thing is just saying if we take the derivative of an integral, we're just left with whatever's on the inside here. That's going to be the answer. The second part down here is a little bit more complicated, and we'll see plenty of examples of this, but if on top it's not just x, if it's a function, like x squared or sine of x or ln x, anything like that, if we have an expression up top, we have to incorporate the chain rule. And I'll show you what this looks like, this whole thing, in examples, but what you do, first you plug whatever expression is on top, you plug it in for the variable, the whole thing. And then the chain rule part, you multiply on the end by the derivative of whatever was on top there. So let's look at a couple of examples, and we're going to work through this entire packet together. But that is an overview of what we're doing. Let me move to, okay. So this first example, if we have a function, f of x is the integral of 1 to x of 1 over 1 plus t cubed, and our goal is to find the derivative of big F. All you have to do is plug whatever's up top. Here it's just x. Just replace the t in the equation with x, and you have your answer. Because, sorry about the dog, she just heard something in the hallway, even though there's no one here. The derivative and the integral undo each other. So if I want to take the derivative of the integral, I just have the expression that's on the inside. The only thing that we have to do is change the variable from a t to an x, because it was an x on top of the integral. Now, example 2 is one of those more complicated problems that use the chain rule. So if we have now the integral from 1 to x squared plus 1 of the square root of t, we need to do two things. First, we need to plug whatever's on top up here. If we're looking for the derivative of this integral, whatever's on top, we plug in to the equation. So the square root of t, if I plug in x squared plus 1 in for t, that's where this comes from, the square root of x squared plus 1. So we plug the expression on top of the integral in to the equation. So I have the square root of x squared plus 1. But because of the chain rule, having a an expression on top other than x, we have x squared plus 1, we multiply the final result by that derivative, by the derivative of whatever is on top. And that's all you have to do. You might have to simplify it, but that's the whole thing. If I want the derivative of an integral, but I have something that looks a little bit more complicated than the first example, you do two things. First, you plug in that expression for t. So you plug in x squared plus 1 into the square root of t. Then the second thing you have to do is multiply by the derivative of x squared plus 1. So we multiply by 2x. So next we're going to look at how these problems look in a multiple choice format. What you should do before I start each problem, you should pause the video and try to find the solution on your own first. And then start the video, and I'll say the answer first, so that way if you got it right, you can skip ahead. So you should pause this video and try number 1 on your own. The answer to number 1 is going to be C. So if you got number 1 right, then you should skip ahead a little bit, skip the explanation, just move to number 2 and try that problem. If you didn't get number 1 right, I'm going to go over it right now. So we're taking the derivative, that's what the ddx means. We're taking the derivative of the integral, and on top we have an x squared. So the first thing I'm going to do is plug x squared into the equation, into this expression. I'm going to plug x squared in for t. Because of the chain rule, I also need to multiply by the derivative of x squared. We simplify. Typically, this part we're going to move out in front, 2x, times the square root of 3 plus x squared squared is x to the 4th. And that's how we get C as our answer. So now, if that makes sense to you, you should pause the video, try number 2. The answer for number 2 is actually C. This problem is kind of weird, but let me show you how to do it. So the first thing we do is we plug in sine for t. So I have 1 over the square root of 1 minus sine squared x. Then we multiply the whole expression by the derivative of sine. The derivative of sine is cosine. If I move the cosine into the numerator, this would be a totally acceptable answer if we're working on free response. But we are working on multiple choice, and that answer is not listed, so it has to involve something else. The 1 minus sine squared, this problem's kind of sneaky because it involves a substitution, like trig identities, like pre-calc trig identities. So the key is that 1 minus sine squared is equal to cosine squared. So that substitution is the one that has to be made to get this final answer, because this is what's going to simplify just to the number 1, because the square root of cosine squared is just cosine, giving us cosine over cosine.